We are happy to have Jean-Luc today. We are happy to have Jean-Luc now speaking about the controversial stuff about our universe that he has been working on.
Great. Thank you very much. Thanks for the invitation. Yes, I guess we'll see how controversial it is, but I want to talk about the no boundary wave function and sort of give a kind of a status update. It's based on many works that I've done mostly with my students at the Max Planck Institute, and there's also a review which you can take a look at if you want more details on some of these things. Let me start with something, just a basic cosmological observation, which is that we don't actually know that much about the curvature of the universe in the sense that it is constrained to be very flat, spatially flat. But in fact, flat is a kind of a funny situation because it could still be open or closed. It could just be closed, nearly flat. If we knew the curvature, we would have much better understanding of the size of the universe. But because it's flat, we don't really know how big the universe is. I mean, there's only a certain part that we can see. The region we see in the CMB, well, it's currently it has a radius of 46 billion light years. But so that's sort of the minimum size of the universe that we can infer, even though when we saw it, the universe was 1,000 times smaller than it is now. But even that part, we of course don't see it anymore, right? This is outside of our current of our current horizon. And so we don't know how big the universe is. We just from the observation of curvature, I'm quoting just one bound. It depends a little bit how many observations you are combining to get this bound. I'm taking a bound here from the Planck satellite, and basically this gives you immediately a lower size for the universe. And it's basically several times, or say 10 times the current Hubble radius. Actually, the figure that comes out most often from these bounds is something like 6 times the Hubble radius. That's the minimum size of the universe. But you can ask, how large do we expect the universe to be? Well, one thing that people thought about for some time was that if the universe had a non-trivial topology, it could in fact be much smaller than we think. But if it did have a non-trivial topology, if you take the universe and you sort of unroll it and you can you actually see this cursor on the screen? Okay, so if you
Yes.
unroll the universe into you would get lots of adjacent domains which are identified, but basically this means that from now a single source we don't see it just once, but we see it from many different directions, and it would just so there would be a certain specific pattern that we should see on the sky. On the right here is an illustration of one of the Weeks manifolds, which also, show that a single object would appear multiple times, and also because the distance traveled would be different, we would see the object at different ages. So again, but these are specific patterns that one can look for, and none of these have ever been observed, right? So we currently think that the universe either has a trivial topology or that the fundamental domain is larger than the currently observed universe. In any case, this means that this lower bound of about 6 times the current Hubble radius is really can be taken seriously. But from the theory side, of course, you can ask how large do we think the universe should be? And if you just go through what happened in the universe, we had a matter-dominated phase. Well, there's the current dark energy-dominated phase, but there hasn't been much expansion during that yet. There's a matter-dominated phase during which the universe grew by a factor of about 1100. Then there's the radiation phase. It depends on how hot the universe was initially, how much expansion occurred. If there was an inflationary period, then of course the size depends on how much inflation there was. But whatever you think of a cosmological, or whatever kind of cosmological model you have, of course, there's a question of how large was the universe before that evolution started. So it comes down to the question of not just how long did inflation last, but also how big was the universe when inflation started. Now, we don't really have much of an understanding of that because in sort of non-eternal standard inflation, one just assumes that the universe inflates, but the initial size is completely arbitrary. In a sense, that's not a complete theory. right? Because it already assumes that there was a universe and that it was starting to inflate, but it's not explaining why this happened. If you have eternal inflation, well, in a sense, you have a mechanism which makes the new bubble universe, by some tunneling event. However, in a sense, anything you try to calculate becomes infinite. So it's really not clear that this is a true physical mechanism. I mean, that physics actually allows this mechanism to occur. And I think it is fair to assume that it is actually not physical because of the infinities. If you take a completely different model of the universe, like a cyclic model, then again, you have sort of a specific behavior that is, that you can describe from cycle to cycle, but you again don't explain how space and time actually arose in the first place. And so again, you have no real understanding of how large the universe is. Okay, that was just sort of as a matter of motivation. What I want to get at eventually is that the no boundary proposal basically gives us a way of describing the beginning of the universe and therefore also of understanding its size. In principle, how far we can go with that, we'll see. This is always phrased in the framework of just the path integral quantization of gravity, where by analogy with quantum mechanics, where you sum over all paths between two events A and B, if you want to calculate an amplitude, then if you include gravity, you sum over all four-dimensional or d-dimensional, whatever. If we talk about our universe, let's say four-dimensional manifolds that interpolate between initial and final configurations. So you have to put in some boundary conditions which specify the state of the universe initially and currently, let's say, and then you sum over all intervening four manifolds and matter configurations on these manifolds. This kind of leads to an infinite regression, potentially, when you go back in time. Because here I'm taking a model where where two spatial dimensions are suppressed and the universe is assumed to have a circular topology. Okay, so this circle here would be our current universe. If we go back in time, which is downwards in this graph, this circle would have been smaller and smaller. But then, of course, you have to put in some boundary conditions at some point in the past, which means you have to have an understanding of what happened in the past. But then let's say you do that and you have the radiation phase, then you figure out there could have been an inflationary phase. Then, of course, you again specify conditions for inflation and you ask what came before and so on. And you could, in principle, keep going back. Hawking's idea that he had of avoiding this infinite regression was to suggest that the geometry should just be rounded off, like so. Okay, if the geometry would be rounded off, not just in space, but also in time, so really rounded off in a four-dimensional sense, then the universe would be completely self-contained. And so this would be a replacement for the Big Bang singularity. And I think the idea, that's clearly what was written also in the old papers. The idea was that if you have this rounding off of the geometry, then you don't need to say anything else. So that was the hope, that you don't need to say anything else about the conditions down here, because there is no boundary. If there is no boundary, the idea was you don't need to put boundary conditions. That turns out not to be quite true, as we will see, but that was the hope. Also, as you know from Penrose's and Hawking's singularity theorems, you cannot do this in Lorentzian geometry. If you have a Lorentzian geometry and the universe shrinks, it will lead to a singularity. But here the idea is precisely that the universe should be regular, and this requires going basically using a Euclidean or in general complex geometry. Then you may ask, how do you define this more precisely? And Hartle and Hawking basically had a proposal, and the proposal was to say that you sum over all geometries that are, in fact, that the definition of the path integral should be that you sum over all Euclidean compact and regular metrics. That doesn't mean that the actual saddle point is Euclidean, but that was their proposal for how you should define the integral. Okay, so if I go back a geometry like this, which is sort of a mixture of Lorentzian and Euclidean, certainly would not be a purely Euclidean saddle point. In fact, because of this mixture, it is complex. But nevertheless, the integral itself could be defined as or at least they hoped that it could be defined as a Euclidean path integral. And note that the wave function of the universe then is just a function of the final boundary conditions, so only of the current size. Because the idea is that in the past, you just sum over this no boundary condition. Okay, so if you have such an integral, which at the time and even now nobody knows how to define in full generality, you can basically you can approximate it by the saddle point contributions. Basically, this saddle point contribution has to be a solution of the classical equations of motion. However, it has to be a solution which is special in the sense that the geometry really should be regular and rounded off in the past. If you find such solutions, then immediately the consequence is that the universe is finite and non-singular. This action will be a finite number. You see, if it was infinite, then of course the probability would be zero for something like that to happen. So one of the first consequences of such a no-boundary idea is that the universe really should be finite, meaning that the size of the universe is also finite. Okay, so we can look at some actual examples of such saddle point geometries. Before doing that, let me say something briefly about the interpretation of the wave function. So as I said a minute ago, the wave function is a function only of the final condition. So in fact, if you want to look at a certain history of the universe, where the universe evolves from one configuration to the next, and to the next, and to the next, then you have to calculate a series of such wave functions. So in fact, for each such configuration, there is one no-boundary instanton. And if my line here is a sort of a sequence of configurations of the universe, then you see at every point on this line there is a no-boundary instanton. So it's not that there is one no-boundary instanton for the entire history of the universe, but rather there is one at each moment. And then you can judge whether this gives a classical universe or not by checking whether the wave function actually behaves in a WKB manner or not. So WKB means that the phase is changing rapidly compared to the amplitude. And just as in ordinary quantum mechanics, if that's the case, then basically this series of configurations obeys a classical trajectory. So you put differently, if the wave function is of this WKB form, you predict and explain the classicality of the universe. So here's an example of a no-boundary instanton. This is the simplest example is to just take pure de Sitter space, which is, from a higher dimensional point of view, is a hyperboloid. So this is de Sitter space in the closed slicing, where each spatial section is a three-dimensional sphere. And this is a hyperboloid, which normally would, re-expand again. And what you can do is at the waist of this hyperboloid, so at the smallest, the smallest radius, you can glue on the Euclidean part of the Sitter space, which is just a four-dimensional sphere. So you can take half of the four sphere and glue it onto half of this de Sitter hyperboloid to obtain a solution where the metric and its first derivative connect smoothly. Okay? If you want to picture this process in sort of a complexified time plane, so now here I'm showing the plane of Euclidean time tau, then you would first go in the Euclidean time direction, starting at 0. You would go in the Euclidean direction, that's this bottom part, the sphere part, and then you would evolve in the Lorentzian direction, which is the Lorentzian de Sitter part. Okay, so you can view this instanton as a path through the complex time plane. Now, this particular solution was special because along this particular path, the scale factor actually takes real values. So the solution is purely Euclidean down here, purely Lorentzian up here. As soon as you add a scalar field, that's not going to be the case anymore. So if I take a scalar field, and now I plot the region by a black line, I plot the region where the field takes real values. Then you see for the scale factor, there's a particular black line, and for the scalar field, there's a different line. If I would put these two graphs on top of each other, these lines would not overlap. Meaning that if I'm in a region, if I'm somewhere where the scalar field is real, the scale factor is complex and vice versa. And generally, both are complex. If they're both complex, we're not going to be able to get to predict anything. I mean, it's not going to give a classical universe, and it will not, in fact, be able to satisfy real boundary conditions at late times. But what you can do is you can change the value of the scalar field just here at the origin, 0. The origin would be this, I'm sorry, would be the bottom of this instanton solution. So right at the bottom, which sometimes is also called the South Pole, you can change the value of the scalar field. And you can tune it such that these lines start overlapping, right? So here is an example where this happens. Now, if you would put the two graphs on top of each other at late times, meaning going up, these lines, the black lines would overlap, meaning that both the scale factor and the scalar field become real values. And this is possible because inflation is an attractor. Okay, so it basically you can have a solution which is attracted to the late time classical inflationary solution. But you see, only at late times does this happen. Near the origin, there is no such black line, and so the fields are complex there. So really, this is a complex solution, which just asymptotically becomes a real solution. Okay, so that's just saying that these instantons exist. But the question is now, how do we, but are they actually the saddle points of the no boundary path integral? It's not enough to just have a saddle point. You have to also know if it's a saddle point of an actual integral. And in order also to know whether that saddle point is relevant or not relevant. Then you get to the question of how do you actually define a path integral? And in full generality, this is not possible to do. But if you restrict your degrees of freedom, so for instance, restrict to just having the scale factor or just having the scale factor and the scalar field, then it becomes tractable. This is called mini superspace to restrict the fields like this. And this is, of course, not ideal because you would like to include the full metric, but it's simply technically not doable, right? So this is the best one can do currently. But then the question is still, how do you define this integral now? Because we said, okay, you go from this no boundary point up to some final field configuration. But in the integral, you still have to say, what is the no boundary point? The most obvious thing to try would be to start at 0 size. So I'm going to use a variable q here, which is the square of the standard scale factor. The reason for this will become obvious in a second. But you see, then the idea is that one just starts summing from 0 size to some given final size. And okay, to keep things simple, we'll just take gravity and the cosmological constant, a positive cosmological constant, just as a model for inflation, essentially. And so, as I said, I'm going to use q, the square of the scale factor, and also this particular parameterization of the time part of the metric. The reason for doing this is that in that case, the action becomes quadratic in q. And if it's quadratic, that means that the path integral will just be a Gaussian, and one can actually do it. So we have 2 degrees of freedom here. We have the scale factor q, and we have the lapse function n. And by doing by using this clever parameterization of the metric, what you can do is you can do the path integral over q exactly. And then you are left with just a path integral over the lapse function, which is a more complicated integral. Okay, so the 1 over q can just be done. And so what one is left with is the following integral, which is just an integral over the lapse n. Here, q1, q sub 1 denotes the final value of the scale factor. So we go from 0 size to this size q1. Well, I should say it's the value of the scale factor squared, the final value of the scale factor squared. And if we want to analyze this integral, then basically we should find the saddle points first, saddle points in n. And these saddle points, well, you can easily see because there's an n cubed and it goes from n cubed to 1 over n. So if you take a derivative with respect to n here of the exponent, you get a quartic equation which has 4 solutions. So there are 4 saddle points, and they are complex valued. Okay, so the actual expression is given here. And so then you can actually plot these saddle points in the complex lapse plane. And there are 4 of them here in orange. 1, 2, 3, 4. There's 2 in the upper half plane, 2 in the lower half plane. And one can look at steepest descent contours around these saddle points. And these, so with the arrows here, they always indicate a direction of descent. And when I say steepest descent contours, this means that the weighting of the integral, so the integrand, the amplitude of the integrand, diminishing as fast as possible. Okay, so this is a way of finding good integration contours for this integral. Then if we have, then we have to decide how do we actually define the integral. These colors here, they indicate regions where the integral is convergent in green and divergent in red. Yellow is in between. Okay, so what you can see is that there is this asymptotic region of convergence out here, for instance, but everything up here is divergent, and here is again convergent, divergent. So it fluctuates. This is simply a manifestation of the fact that you have this e to the in cubed part. So when n gets large, there will be regions where this e to the in cubed blows up, and regions where this e to the in cubed goes to 0. And in green is where it goes to 0, in red is where it blows up. So if we want to have an convergent integral, then we must start and end in one of these green regions. And there's a singularity at 0, so one can either go from infinity to infinity, or one can start or end also at the singularity. The singularity comes from this 1 over n factor here, so it's e to the 1 over n, so this is an essential singularity at 0. If we have an real lapse integration contour, meaning that we define the integral to sum over Lorentzian metrics, then one can deform this, just using Cauchy's theorem, if you like, one can deform this contour to go through this saddle point number 1. Okay, and in fact, one can deform it to the steepest descent line that goes through this number 1. And the arcs here at 0 and at infinity give 0 extra contribution. One can check this explicitly. I'm not going to go through the details here, but so this contour can just be deformed to this steepest descent contour J1. And so in fact, this saddle point 1 is the one that contributes to the integral. And it's the only one. That would be the integral would then be essentially defined on this J1 integration contour. If we think back to the original proposal of Hartle and Hawking, they wanted to sum over Euclidean metrics. But you see, Euclidean metrics would mean imaginary lapse function. And for imaginary lapse function, there's a divergence up here. Or if you want to only define it on the lower half line, there's a divergence near 0 here. So whichever way you do it, there is a divergence, meaning that the Euclidean integral, in fact, just doesn't exist. So it's just not possible to define the Euclidean path integral for gravity. And so you are forced to do something else. For instance, to try the Lorentzian integral. Now there is a problem with this saddle point. So from this calculation, where we've just looked at the scale factor, everything looks fine. But if you include perturbations, it turns out that that saddle point is unstable. Meaning if you include perturbations, the likelihood for bigger perturbations is bigger. So you predict that there should be more and more perturbations, meaning that the universe should be more and more curved and should actually collapse. Or put differently, in fact, you cannot normalize the wave function anymore, because for large perturbations, you get an unchecked growth of the probability, of the weighting. It turns out that, in fact, both of these saddle points in the upper half plane are unstable, and the ones in the lower half plane are stable. But these ones were simply not reached by this Lorentzian contour. Let me just explain this maybe a little more. There's kind of an ambiguity in the sense that, because it's quantum theory, you cannot impose compactness and regularity at the same time. If you want the universe to be compact, you want it to start at 0 size, so you should impose a equals 0. But if you want it to be regular, then when a is 0, the Friedmann equation still has to be satisfied. And that means that you would have to if I write out the Friedmann equation here, you see that when the scale factor goes to 0, I'm left with the condition a dot squared plus 1 is 0, which means a dot has to be plus or minus I, which is nothing else than this condition that the universe should be Euclidean in order to round off. But there is an ambiguity in the sign here. It could be plus or minus I. And you can think of this as the choice of Wick rotation. So, when you do a Wick rotation in quantum field theory, you also rotate the time to Euclidean time in order to get convergent integrals. But if you were to rotate the other way from the standard way, you wouldn't get Gaussian integrals, you would get inverse Gaussians. You would get something that blows up. Instead of getting something like e to the minus phi squared, you get something like e to the plus phi squared, right? And that just doesn't make any sense. The trouble that we had here is that we get both of these choices because we were just imposing that the universe starts at 0 size. We cannot at the same time put a condition on a dot, which would be a momentum, right? Because it's quantum mechanics, a and a dot don't commute. You cannot impose a condition on both of these at the same time. It's either one or the other. And so we got both stable and unstable saddle points, or in a sense, correct and incorrect Wick rotations. And it just turns out that when you define the integral by a sum over Lorentzian metrics, you pick up the unstable saddle point. This is a very general feature here because the Einstein equations are real valued equations. And so if we have a complex solution, like this one of these no boundary solution, then the complex conjugate is also a solution, necessarily. But you see, if that means that the action of one solution is a complex number and the action of the other solution is the complex conjugate number. And if you put this in, the saddle point contribution, e to the IS, then you see that the weighting changes sign. So if you had something like e to the minus phi squared, you get e to the plus phi squared. So both are always there. And this is a problem, right? Because there's always something unstable then that's present. Okay, here's an illustration, but I think I already said all of this. Now, there is a way around this, which is to do the opposite, to go to momentum space, if you like. So instead of saying we impose that we start at 0 size, we could just say we fix the initial expansion rate. And if we fix it, you see here we had this issue, this condition that a dot, it could be plus or minus I. Now, if we fix a dot initially, we can choose the correct sign. We can choose the correct Wick rotation. And so, okay, so we work with this variable q. So q dot over 2 basically has to be plus I. Of course, we're changing the philosophy a bit because we're saying we want to sum over metrics that start Euclidean, and we're not saying anything about the size of these universes. So they could already be non-zero size initially. We're just summing over all universes that start out Euclidean. So if you do that, something funny happens, which is that these saddle points, the unstable saddle points in the upper half plane are simply gone. And we're just left with 2 saddle points, which are the stable ones. And so now the integral actually contains stable perturbations. And it turns out that at the saddle points, the universe also happens to start at 0 size. So we recover precisely these no boundary instantons, but putting a condition on the initial expansion rate rather than on the initial size. It seems to say that this regularity condition is more important than the condition of compactness. Now, if one does that, there's a nice side effect, which is that the perturbations are not only stable, they are also automatically in the Bunch-Davies state. I don't really have time to go through that now, but basically what it is saying is that precisely the perturbation which remains regular, where the instanton is rounded off, one can show that that's exactly the Bunch-Davies state. So you don't have to explain why you use the Bunch-Davies state. It's automatic here. And if you now calculate the probabilities for different kinds of evolution in a scalar field potential, say, you find that it scales, that the probability scales as e to the 1 over the initial value on the potential. So this SP stands for south pole. So phi SP is the value of the scalar field phi at the south pole, so at the bottom of this instanton. But if it's an inflationary phase and it's slow roll, then the scalar field doesn't change much anyway. So that value is also the value, approximately the same value as a bit later on. What it's saying, though, is that you see it goes as e to the 1 over value of the potential. And this is a problem because it means that if you are lower on the potential, you get a higher probability. So if the universe starts lower on the potential, that's more likely. But if it starts lower, that means inflation is shorter. And so, in fact, you predict that it should be as short as possible, meaning just maybe a couple of e-folds. Nothing like the 60 e-folds or so that are required to explain the flatness of the universe. From that point of view, this is simply not working. Then the question is, what do we do about that? And a possible answer has come from maybe unexpected source, but let me talk about that. And the issue is, with these complex fields and complex geometries, should we really allow all of them? Right? There's a question of what kind of metrics should one actually sum over? When I was talking here about these definitions of path integrals, really these paths along in this complex lapse plane, all these geometries are complex. The question is, are these really all allowed? Do they make sense physically? Now we know that certain complex or Euclidean or complex in general geometries really do make sense. Like if you take a Schwarzschild black hole and you take the Euclidean version, then it becomes a smooth manifold if you assume the correct time periodicity in Euclidean time, and that periodicity immediately gives you the Hawking temperature. So there's clearly something physically reasonable about this complexified geometry. If you do this with a rotating black hole, in fact, it doesn't become just Euclidean, it becomes fully complex because of this dt d phi cross term in the metric. Right, so you pick up an I here. And these things are clearly make physical sense. In fact, it's the fastest way of calculating black hole temperatures. But at the same time, you can also quite easily make complex solutions that are nonsensical. For instance, just take flat space, ordinary flat space in 4 dimensions, but written in these polar type coordinates. This is just flat space. But r here is a radial coordinate, which normally runs from 0 to large, well, goes from 0 to infinity, and takes real values. But you could just as well do a coordinate change and let r be a function of some fiducial coordinate u. So r is now just some function of u, and you can now choose a curve for r. So for instance, you can take a curve like this, which goes from large negative real values and reaches large positive real values, but near the origin, it goes into the complex plane. This means, so this kind of a path actually describes a wormhole, because on both asymptotic ends, it's just flat space, but in between, there's a complex value tunnel. Nevertheless, you see, this is just a coordinate change from ordinary flat space, and so actually it will still satisfy the vacuum Einstein equations. And it has zero action in particular, because, the Ricci scalar is just 0. The exact same weighting as a classical solution. So these wormholes should be everywhere, if they exist. Evidently, they don't exist, because they would, they would be here all the time, everywhere, because they're just as likely as any classical evolution to occur. So there must be something wrong with these. And so this is already saying that clearly not all complex metrics can be included. But now we have, examples of complex metrics that are fine, and an example of a complex metric which is not fine. So what's the actual criterion? And so one proposal for a criterion was made by 2 mathematicians, by Kontsevich and Siegel, but in the context of ordinary quantum field theory without gravity. What they were interested in is quantum field theories on curved spacetimes, and in general even on complex spacetimes, because they want to use this to define quantum field theories. So their idea is that maybe you can define quantum field theory actually better on a complex spacetime and then take a limit where you let that flow to Minkowski spacetime. The advantage would be that on a complex spacetime you get better convergence properties. Okay, so that's their idea for how to define quantum field theories. What they show, or what they require rather, is that any matter content that's given by p-form gauge fields should have a convergent path integral on the background. So the metric must be such that if you calculate a path integral, the integrand must be convergent. In particular, the modulus of e to the is should be less than 1. And the reason for focusing on p-form gauge fields is that these are basically the only fields that you can have that have a local covariant stress-energy tensor, as implied by the Weinberg-Witten theorem. Okay, so these would be the most reasonable type of matter fields that you can normally have. This at first sight sounds a bit daunting, but it turns out that if you write out this condition, what it means for the metric, it's surprisingly simple. So the idea is that at any point you can always diagonalize the metric. And it just has these lambda factors as in the diagonal. Okay, if you write out your metric, this is just at any point you can do this. You cannot do it globally typically, but you can always do it pointwise. And then basically you write out all of these conditions here for all p's. And then it's actually quite short, but you have to write it out to convince yourself. You see that what you find is that basically these lambdas cannot be too complex. They can be a little complex, but not too much. In fact, the sum of their arguments has to be less than pi. If that's the case, then the metric is allowed in the sense that all of these p-form fields will have a convergent path integral on the manifold. Now, one funny thing is that ordinary Minkowski space is already at the boundary of this, already saturates this inequality. Because for Minkowski space, you have this minus dt squared. Okay, so there's a -1, which has argument pi, and then the others are spatial directions, which have argument 0. But so the sum of arguments is already equal to pi. So basically, this inequality here is saturated for Minkowski space, which is, of course, understandable because in Minkowski space, the Feynman path integral is precisely only conditionally convergent. It's e to the I times something. It's not manifestly convergent. And so when this inequality is satisfied, you have something that's manifestly convergent. And then when you reach when you saturate it, it's only conditionally convergent. Okay, so you can easily regulate this by just putting in an I epsilon, but you have to, and this is the same as the standard I epsilon prescription, you just put it in the metric instead of into the propagator. The only thing you have to pay attention to is the fact that, you can do this I epsilon more or less in, either with plus or minus I epsilon, but what you cannot do is you cannot cross this line. You cannot go from positive to negative epsilon, because that would violate the inequality. Now, it turns out that that's precisely what immediately eliminates these kind of complex wormholes. You see, because if you have a wormhole, well, not this condition here. I mean, the Kontsevich-Siegel condition in general immediately eliminates the wormholes, because when you cross the imaginary axis here, r takes an imaginary value, meaning r squared becomes negative, and at that moment, all of the spatial directions have argument pi. So you get for all of the spatial directions already a contribution of pi to this sum of arguments, and so you will obviously violate the condition. So you see, this condition does seem to be quite sensible in the sense that it already eliminates the one example that we looked at that we knew was pathological. And you can also check that this condition allows for the complex black hole matrix. Now, then you can ask, okay, what happens if you now look at the no boundary instantons? Do they satisfy this criterion or not? One thing one can estimate is how large is the imaginary part of the scalar field near the bottom of the solution. This is something that you can easily estimate, and you see it's actually given by the steepness of the potential. So it's proportional to v comma phi over v. Now, that means that if this potential is steeper, the solution will be more complex. And you can already guess then, and this is what turns out to be true, if it's too steep, if the potential is too steep, the solution is simply not allowed. So you must be in a part of the potential where the potential is flat, which in fact is precisely what you want for a long inflationary phase. To analyze this in more detail, what one can do is one can just plot on these complex time plane curves. You see, you can plot in red here the curve where this inequality is saturated. So in red, I just plotting the curve where this Kontsevich-Siegel criterion is saturated. And if you stay below or to the right of this curve, you're fine. If you go to the left, then it's not allowed. So if I have a solution which ends up here, just on the right of this curve, or just below this curve, basically, then that's a geometry which satisfies the Kontsevich-Siegel criterion. If you end up above, then it's not allowed. Okay, so what I'm saying is this is a method for checking numerically whether instantons satisfy this criterion or not. If you do that, what you find is that there's a minimum number of e-folds that you need. That's the interesting part. Because you have to be in a part of the potential which is flatter, you need a certain minimum number of e-folds. But of course, it depends on the potential. So here I'm taking an example of potentials of this form. That's the natural inflation form, 1 plus cosine phi over f. F is just some constant that determines how steep the potential is. And it turns out for different f, you get different minimum numbers of e-folds that are required. Okay, so for instance, when f is 4, you see that you need something like at least 22 e-folds. If f is 6, it turns out you need at least 60 e-folds of inflation in order for a solution to be allowed. That's interesting because it means that now you are not predicting to be as low on the potential as possible because you also have to be in the region where it's allowed. And so the steeper part, which is lower on this kind of inflationary potential, is just not allowed. And you have to be in the allowable region further up on the potential. Of course, because there's this general probability which is higher for being lower, you find that the most likely point is that you are basically just allowed. That basically the minimum number of e-folds is also the most likely number of e-folds. So what you find now is a correlation between the number of e-folds and the potential, and then also the predictions for this potential. So there's an extra connection between all these numbers. So if you look at the spectral index and the running, there's a correlation between all of these. So here, what we're plotting is the dot is always the minimum number of e-folds that's allowed. And it's showing that if you want to have, in this kind of class of potentials, if you want to have a potential that's in agreement with current data, you need f to be at least 6. But if f is at least 6, from this plot, you see that the number of e-folds that you need is at least 60. So this means that if you've explained one more thing, you can either say, okay, I've explained the number of e-folds based on matching a spectral index, or the other way around. You can say, I match the spectral index, and then you explain, or you match the number of e-folds and you explain the spectral index. Either way, it's one extra explanation that you gain. An additional consequence is that because the most likely number of e-folds is also the minimum number of e-folds, the universe is then expected to be comparatively small. You can check, what kind of size would we expect? Well, now we have a nucleation size, which is given by the no boundary solution. We have an inflationary phase where the number of e-folds is fixed, again, by the no boundary instanton and by this criterion of allowability. And then from that, of course, because if you have the size of the potential, you know the reheating temperature, and then the subsequent evolution is fixed. If you put all this together, it's quite amazing, but you then precisely find that the universe should be not much more than the currently observed part. It could still be, a couple of orders of magnitude. These estimates are not so precise. So it could still be a couple of orders of magnitude bigger, but you find that actually it should not be too much bigger. That means that, in fact, you would expect that the curvature is, well, closed, so that basically the universe has closed spatial sections, but they are not. But this curvature is potentially observable. This is a little bit, well, it's not. One cannot make a very precise prediction, but you sort of, from this argument, you expect the universe not to be, significantly larger than the part that we've already observed. Now, let me just to end. Let me just go back to these definitions of path integrals, because there's also a funny thing that happens there. If you now look at these definitions of path integrals, do these metrics that we're summing over, are they satisfying this allowability criterion or not? So I've taken the two cases that we discussed at the beginning of the talk, one where you start at zero size, that's here on the right, and one where you start with Euclidean momentum, Euclidean expansion. In green are geometries that are allowed, in red, geometries that are not allowed, and in blue are the saddle points. And so what one can see, what's interesting is that these no boundary saddle points in each case lie exactly at the boundary of the allowed region, which to me is not completely clear why this should be the case, but it's just an observation. I don't think that this is a coincidence, but there is currently no good explanation for this. What it does mean is that the definition of the path integrals would still have to be modified, because you see what happens now, these black lines are steepest descent contours, and they get cut off basically by these red regions. So, for instance, in this case, where you would like to define the integral using these full steepest descent contours, you can only use half of them up to the saddle point, and then they would be cut off. So it's not completely clear how you should properly define the path integral. But it is interesting that the no boundary saddle point is sort of just on the border of the allowed region. A bit like Minkowski space is precisely on the border of the allowed region in this Kontsevich-Siegel construction. So I think this is something that one could try and explore in the future. Okay, so in this talk, I reviewed how one can at least attempt to construct path integrals with no boundary initial conditions. As we saw, it's not so trivial to just impose this condition of having this rounded off geometry. You cannot, for instance, impose that you start at zero size. Rather, you should impose that you start with Euclidean momentum. So in some sense, the wave function of the universe wants to be in momentum space rather than field space. If we add this condition of allowability, then it eliminates a large number of possible solutions. And in fact, what it leads to is that for a given inflationary potential, it gives you a minimum number of e-folds of inflation that are required in order for the solution to be allowable. And in that case, you predict that the no boundary wave function predicts that the universe should have undergone precisely this minimal number of e-folds of inflation, which, as a further consequence, implies that the universe should be comparatively small. Of course, still large, it has to be, of course, large already in order to be in agreement with observations, but perhaps not so much larger than the part that we've already seen. Thank you.
Maybe we can start questions if anyone wants to ask.
Sure. Can I ask a question? So just a general question about the logic. So usually path integrals are close to the saddle points because you have some sort of a weak coupling expansion. You're expanding about something, otherwise the one loop corrections would be bigger. So what is the expansion here that's letting us stay close to the saddle points?
It's Planck's constant. So it's you always have the e to the I over h bar. times action. So when h bar is small, which it is, then the saddle point approximation should be good.
So
Basically,
it's the
the
Q that you
action.
had in the denominator in the mini superspace. You're saying that that thing is big. I mean, because the size of the universe is big in Planck lengths. That's the expansion.
So the action is big. The action divided by h bar is very large.
The action is big, and is that enough to say that the perturbation, that the one loop correction is small if the action is big?
Well, as long as the curvatures, yes, and in fact, what you want also is that the curvature of the universe should be small compared to Planckian curvatures. That's the further requirement, which is because of the non-renormalizability of gravity, right? Because you would get additional terms in r squared, r cubed, and so on, and so you want this can only be applicable if the curvature is small. But in this case, because for realistic inflation, you are many orders of magnitude below the Planck scale, this is always the case.
Okay, so it's just because you fed in the initial scale, or because we were restricted to the mini superspace where everything was homogeneous in the first place, or how did you?
Well, that scale comes from the assumed potential, right? So you assume an inflationary potential, and because that's small in Planck units, the saddle point solutions that you find also have small curvatures.
Okay.
Nevertheless, in Planck units, the action is very large, and that's why you can do a reliable saddle point approximation.
Would it be the same to say that you're doing quasi-classical description, or?
Yeah, it's semi-classical gravity, basically. Yes, but you see, there is a quantum part in the sense that the solution is not a real solution to the Einstein equations. The saddle point solution is a complex solution. That's what incorporates basically this nucleation of the universe from nothing.
So the potential doesn't get renormalized? I mean, you start with it being small and it will never get to Planck size.
I mean, in principle, you could calculate corrections, of course. But here, because you are already quite far from the Planck scale by assumption, what you also find is that it's sort of self-consistent in the sense that what you find is that you want the potential to be flat in order for this allowability criterion to be satisfied. And if the potential is flatter and you still want to match the observed size of the fluctuations in the CMB, the energy scale has to be lower. So you are automatically, so in that sense, it's the calculation is self-consistent because you are driven precisely to those potentials which are small in terms of their energy scale.
You're driven to but the potential you put in by hand, though, no?
Yes, but there could be parameters in the potential that allow it to have different sizes, different heights, different steepness, and so on. What I'm saying is the solutions that come out as preferred are the ones where the potential is flat. And then if you put in the additional outside condition that we've already measured the size of the fluctuations in the CMB, and then you want to match these, then the energy scale of the potential will automatically have to be low.
Oh, okay. So you're saying if you had some parameters, then observations suggest that this thing should be very fine-tuned to be small.
Yes.
Okay.
That's what the general cosmological observations say anyway. And now here, the advantage is that that's also what this allowability criterion is saying.
Okay, thanks.
So the assumption is that we want to do quantum gravity with starting from Einstein-Hilbert action. We don't want to modify it, right?
Well, in principle, of course, there will be, because this is quantum gravity, there will be corrections, right? So if you do this perturbatively, there will be, r squared, r cubed, and so on, all these terms, but they will not be big, precisely because the curvatures are small. So these solutions have, with the kind of potentials that I was using here, the energy scale is something like 6 orders of magnitude below the Planck scale, meaning the potential, which is the fourth power of the energy scale, is something like 24 orders of magnitude below. And so this is very small. So if you take these corrections are then automatically come out as small. I should also say, this calculation was done in 4 dimensions. You can try and do the same kind of calculation also in a higher dimensional context. You can add extra dimensions, you can add fluxes, you can do this in string theory, but I haven't done the associated calculations of allowability there, right? I'm just saying this is sort of, in some sense, this is an effective description of just the 4 dimensional universe. But in principle, of course, you should try and do this in a more fundamental context. Yeah, but I think the idea is that, well, the idea is that this is already a good approximation.
I'm trying to understand this allowability criterion. So in the case of the wormholes, you told me at negative r, I should have phases which are pi each, and so you get pi d, and it's bigger than pi, obviously. Why don't you get minus pi? Are the phases fixed to be between 0 and 2 pi? Is that the fundamental domain? Is that the reason they can't be minus?
Okay, it doesn't matter because you take the absolute value. The criteria,
Oh, there's an absolute value,
yeah,
right?
there's an. I didn't say that. There is actually an absolute value in the.
Oh, okay.
Here it is.
Okay, I saw some equations without absolute values. But
yeah,
then,
I'm sorry. I realize now that I realize
Okay.
now that I forgot it in the other in another slide. There
okay.
is in fact an absolute value of arguments that you must take.
Oh, okay.
It turns out, so when you derive this criterion, you do it for different p forms. And so, for instance, if you did it just for the, I think just for scalars, you would find this equation without the absolute value. Then you do it with one forms, and you find one minus sign in this relation when you like here. Sorry, no, with the scalar there's already one minus sign. Then if you have a mass term, you have just the sum of terms. Then you have a scalar, you get a minus sign. You use a vector, you get 2 minus signs, and so on. When you put all these conditions together, you see that they're satisfied if you put an absolute value there for each term. Anyway, I'm sorry. I realized that now that you say it, I didn't have the absolute value here. I should put it there.
Okay, thanks.
But of course, it doesn't matter how you define your argument and so on. The idea is simply that you have this e to the I times kinetic term of some field, and you want that thing to not to blow up. It's basically, this is the criterion. And because you have these metric factors that come in here to just contract these indices, the important point is that this thing must be positive so that you get an e to the minus something, so that when the fields become large, the contribution to the path integral becomes small.
Also, I missed if you answered this, but you said that Hartle and Hawking chose, to start with the universe being infinitely small because they didn't want to have a second boundary condition on the path integral. And then you said, well, people tried to do that, but it didn't work so well. So instead, you replaced that condition with, because you had the first derivative being imaginary, you replaced that with a condition on the first derivative. And so then, in principle, you could be back to having an initial boundary, but then you didn't talk about, or did you talk about how to fix that initial boundary?
Well, so what I said is that the way this turns out is that at the saddle point, the initial size is 0. I said it briefly, but maybe I should have emphasized it more. You now sum over all metrics that start out Euclidean, but that have, different sizes. At each point here in the complex lapse plane, you have a different initial size. And then it just so happens that at the saddle points of the path integral, the initial size is also 0. So the saddle points, in fact, remain unchanged by putting in this condition rather than starting at 0 size. I can also say it differently. If you start at 0 size, in principle, you could have any initial expansion rate. And in that case, it turns out that at the saddle points, the initial expansion rate is precisely Euclidean and such that the solution is regular.
Okay, and then we don't run into that problem. So you were telling us in a quantum theory, we can't fix Q and Q dot at the same time.
Yes, exactly.
So you're telling me that you are fixing Q, but not fixing Q dot because it's for any Q dot? Or
I'm saying here I'm fixing Q dot to be precisely such that the initial expansion rate, so that the Friedman equation is satisfied. And then it turns out that at the saddle point, the initial size is also 0. It could have this could have turned out differently.
Okay, but how is this consistent with the uncertainty principle now, since you end up knowing Q dot and Q at the same time?
That's just at the saddle point. So the saddle point, right? So I mean, I'm saying for any of these solutions, I can, of course, figure out what the initial size is. At each one of these points here in this complexified lapse plane, this condition, Q dot over 2n is equal to I, is satisfied. But they all have different initial sizes. But then precisely at those two locations where they have the orange dots, the initial size is 0. And those turn out to be also the saddle points of the path integral.
Okay, so so that doesn't mean that your actual state has both Q and Q dot being known. Is that how you get out of the uncertainty principle bound?
I would say there's an uncertainty in the initial size. It's just the most likely value is 0.
Yeah. Okay. But yes, most likely, but also you're very close because of this argument you just made before.
Right, exactly. Yes. So in a sense, you cannot really know. In any case, in this situation, when you look at the wave function, it only starts becoming of WKB form once the universe has reached a size that's already on the order of the Hubble radius of the inflationary phase. So for smaller sizes, you cannot even say that there is a classical space-time. So in a sense, you run into the uncertainty principle already before getting to 0 size. You already run into it when the universe reaches the Hubble radius of the inflationary. Basically, if I go back to these very early figures, when the universe itself is of this size, the waist of this de Sitter hyperboloid, it's only when it is of this size and bigger that the wave function actually turns out to be of WKB form. If you try and ask what happens when it's smaller, when you're down here, the wave function is completely complex, and you cannot make predictions for classical values of the fields.
So when you say that at time 0 the size is 0, that would naively imply that infinite energies are allowed in the system. Is this something that you kind of are able to put an upper bound on, or you just consider it not to be an issue?
So, for instance, I would not say that at time 0, you see, this time, you should see it as a parameter. Really, what matters is the wave function depends only on this final configuration. And so you can only infer predictions for observations from the wave function. So only from these, and the wave function is a function of final configurations, and it only predicts that you have a classical space-time when the space-time is already of a size that's at least the Hubble radius of inflation. So what you would like to check is something that one cannot actually check. Maybe that's a self-consistency of the model, because you cannot, if you say, okay, if you try to look at the wave function when the size is near 0, it's a fully quantum state, right? For instance, you cannot say that the universe already has a classical space or classical time.
But you nonetheless assume that in some form quantum mechanics applies below this waistline.
Well, I would say, you see, the instanton is just a way of calculating the wave function. You should then use the wave function to infer what the universe is doing. Once the universe is big enough, basically what you infer is that it undergoes classical evolution according to Einstein's equations. But that's only once it is already of a size that's at least the Hubble radius of inflation. If you try to go to smaller sizes, you don't get something very meaningful.
By the way, like another question, I mean, I understand that there is probably not a good answer to it, like ever, but do you think that the size of the Hilbert space of the universe below the waistline is infinite, or whether it's finite? I mean, what would your intuition be about that?
Oh, I don't know. I mean, so there are, of course, there are arguments. De Sitter space, here we are basically looking at a gravity with a cosmological constant, where the standard solution is a de Sitter solution which has a horizon and therefore, has an entropy which is a quarter of the horizon area. And if you take that seriously, then the Hilbert space should be, the exponential of that. In the dimension of the Hilbert space should be the exponential of that. But this is a simple model, right? This is So I would not, for instance, say that that's completely realistic to put in a cosmological constant, or even if I put in a scalar potential, this will have to be figured out by the eventual full theory of quantum gravity.
Yes, yeah, that makes sense.
Right? I mean, it's because here we don't, let's put it differently. The way I see this is I don't see this as describing the ultimately correct microphysics. You know, if we have the Einstein-Hilbert action and we have a scalar field with a potential, it's not clear that those are the correct degrees of freedom to describe all the microstates. But for that description, it seems that the entropy argument suggests that the dimension of the fundamental Hilbert space should be something like e to the horizon area divided by 4. But I think really it depends on what quantum gravity will end up being.
Yeah, but this is good intuition enough. Thank you.
There's one more thing to say about that, which is a bit funny, which is that, in the zeta space, the horizon depends on the observer. It's not like a black hole where the horizon is just, where the black hole is. But in the zeta space, every observer has their own horizon. Depends on where you are in the space. If you have two observers which are far apart, they have different horizons because the horizon is always centered on the observer in the zeta space. So this is saying that actually the fundamental description should depend on the observer.
Well, that sounds very quantum mechanic-y,
Yes.
right?
Yes.
Interesting. Can the horizon be zero for any observer, or is there like any limitation on the variability?
The horizon is just given by the value of the cosmological constant, which determines how much the universe expands. I mean, how strong the acceleration is, and then that determines where the horizon is.
I see.
There is still some transitivity, right? If I can't see you, then you can't see me. There can't be an overlord who sees everyone and no one else can see them, right?
That's right. That's right. Yes. So the descriptions have to be consistent ultimately between people who can see each other.
More philosophical question, just about you mentioned that somehow there is resolution to this situation that you have the probability of the existence of universe is bigger than zero, and therefore the universe is finite. But that this interpretation of it, would it be to say that if you have a consistent theory for which a universe is finite, therefore it's probable, it also comes with some sort of probability of other universes popping up?
Yes.
So, yeah, is there any kind of way to look at a bigger theory where you control over, like you have some control of an ensemble of universes, or it's the formalism takes care for each universe separately and doesn't know about others?
Yeah, I mean, this is completely unclear, I would say. But you see I mean, it comes back to the standard question of interpretation of quantum mechanics, because in a sense, it's the same with any experiment you do. What happened to all the other possible outcomes? Are they still there somewhere or not? Is there another version of me that saw a different outcome and is still existing in some, completely separate universe or not? Now, it's the same question, really. And I don't know. I mean, obviously, I can say anything because it's impossible to prove or disprove, right? So that makes you think that actually there's something missing there. Also, seems to me that one should get rid of infinities as much as possible in physics. So I don't like the many worlds interpretation from that point of view, because you get an infinite number of worlds to explain one. That seems complete overkill. I do like the idea, Everett's original idea of a relative state. So you basically you describe the universe relative to your state, and you see what the possible outcomes are. But then, in some sense, wave function collapse, it seems to me, has to occur somehow. If only if you see it as kind of updating the information you have about the universe.
Yeah, I mean, to me, this would be more natural to have some sort of a framework where, for example, like as we know, there can be many particles in the universe, right? And we have a field theory that says that if you have enough energy, you can create several particles and so on. in the same way, if you could have some quantity that quantifies how many universes could actually be created or something, then it would make a bit more sense. If it's like infinite, then it becomes, as you say, a bit overkill.
Also, I mean, we know that normally you should only talk about things that are in principle measurable. Always get into trouble if you don't do that. So if you cannot have an experiment which would show that there are other universes, then you should not ask the question. First, sort of think of a way of how you could make a measurement that would convince you that all these other possibilities exist. And if that cannot be done, then presumably it doesn't make sense to talk about them.
Yeah, so related to that, maybe not much related, but a similar question about measurability. So the taking complex metric comes with the natural question of what happens to distances, and if we also complexify space, like we probably don't, because from what I understood, we are doing four-dimensional field theory, gravity, and that's always staying the same manifold and stuff. It's just the metric is becoming complex.
That's right.
But then the distance becomes complex, right? If you're taking complex metric.
Well, I think the proper way to view it is that this is a way of calculating the wave function.
Yeah.
Wave function itself has as arguments only real values of the fields. So in the actual universe, then the distances are real. These complex metrics are, in a sense, just, they help you in calculating the wave function. I realize it's different in this Kontsevich-Siegel approach where they really want to have a quantum field theory on a complex manifold. But then again, also in their approach, right at the last step would be to take the limit of going to Minkowski space, and then everything becomes real again.
What is this approach?
Well, it's just that they try to have a sort of a better definition of quantum field theories, where everything is more manifestly convergent. And so they want to put the fields on a complex manifold for which convergence properties are better.
Can you mention a reference?
Well, it's this paper. I don't have the reference. I don't know it by heart.
Yeah, maybe later. I will ask.
It's well, I can send it to you.
Yeah.
The paper is quite difficult to read, I should say, though, because it's written by mathematicians. So the language is a bit unfamiliar to physicists.
Can I ask a question?
Hi, Kelly.
Hi. Yeah, when you say the universe is finite, I'd like to understand as contrasted to what? Presumably in a de Sitter space, the spatial sections are compact anyway.
Yes, but if you have something like eternal inflation, then basically the universe is infinite in size.
Well, that means as it goes on in the future, right?
No, already at a finite time.
Meaning there's more out there, right?
Yes.
Presumably,
yes.
With respect to in other bubbles.
Yes, and also in some cyclic models, there's implicitly the assumption that the universe is infinite in size, and that everywhere it undergoes cycles. And also, or let's take a brane world model. The branes are typically taken to be infinite.
Well, okay. Oh, they may or may not. That's just
you have to. Maybe you could, of course, change the topology, presumably.
But so at one level, you were adding up a whole bunch of these sort of drinking glasses and taking a sum over them. And what you're now considering is some sort of effective theory universe as a result of that sum. And you say that's finite. But you actually have all the other ones. You had a little railroad train of these things that you were adding up a while ago in one of your slides.
Now that was just to show that at each moment in the evolution of the universe, there would be one such dominant saddle point.
Okay, but are you really saying that there are no other bubbles?
No, I'm not saying. I mean.
Or just that the bubble
not in this simple model that I had here.
Okay, well, let's take that. I understand that. So just take this one.
Yeah, not in this simple.
Oh, in this simple model, there are no other bubbles.
No, you mean can you have Coleman-De Lucia tunneling events and then other bubbles? Presumably yes, but you have to wait for a while. I mean, their probability is not very high.
Well, I'm in the what do you call Andre Lucas type of eternal inflation, there are other bubbles that are presumably out there in outside light cones we can't see, corresponding to universes that have bubbled away, and we're just not in connection with them. Are you really? I don't know what is. What I'm not understanding is what is the infinite that you're comparing finite to?
In this case, it's simply that you want the action to be finite.
Yes, right. I'm sympathetic with that.
Yes, and so a simple way of having the action not being finite is to have an infinite volume of space.
Yeah. Okay.
In that sense, that's simply what I meant.
Space, time, or space?
Space. The action always has a spatial volume factor.
3 slices. Yeah. Okay.
Yeah. And
But
so
ordinary de Sitter space does that. So, and that's what we seem to have from observations.
No, because you can have de Sitter space in the flat slicing, where the spatial sections are basically just flat space. And that could be infinite.
So are you then saying there's a preferred slicing
Yes. So the no boundary proposal would automatically predict the closed slicing to be the relevant one.
I see. That's the point.
That's one way of saying it, yes. And that's why you would also predict that the curvature is non-zero. So we may see it as being small due to the big expansion of the universe, but it should, fundamentally, it should be non-zero.
And are there observational consequences of having a preferred slicing?
Well, for instance, so what I was saying at the beginning of the talk here, if you put in all the stuff that we know about the universe.
Oh, excellent. Thank you.
Right? You have this, you have then you have whatever, the energy density in matter, radiation in the scalar field, or dark energy, whatever it is. And then you have a curvature term. And so this curvature term is currently predicted to be very small. No, sorry, observed to be very small. But what I'm saying is the no boundary proposal would predict that it is actually non-zero. The question is, at what point should you see a deviation from zero? This depends on how much inflation, in these models, this depends on how much inflation you had. So this is something that is potentially observable, but there's sort of a fairly narrow window, because right now it is being observed at the percent level, and one can go down by another 2 or 3 orders of magnitude, and then it gets very hard to measure because of the fluctuations in the CMB, which basically are, they have their own curvature, which is superposed on this, and so to disentangle that is probably impossible. So there's a window of another 2 or 3 orders of magnitude that could observe this a non-zero curvature, and if it's not there, then we may never find out.
So why do we need a non-zero curvature in order? I mean, this should be obvious, but in order to have a finite size, I mean, can't we be on a 3 torus or something?
Of course. I'm saying the no boundary proposal predicts a non-zero curvature because of this rounding off. This rounding off only works if you have curvature.
Oh, you can't round off the 3 torus.
Not like this, no. Yeah, no, you can't do that. The 3 torus is rounded off in space, but here you need to round off in space with the time direction included too.
Yeah. No, I realize you would get it. I mean, if you just look at the cone over the 3 torus, it's got some singularities in it. But on the other hand, you're not going down into the past the Planck scale anyway, so I don't know if you really care about that, but maybe it would.
I mean, you could maybe you could round off each S1 separately. First one, then another.
Yeah, you consider the smash, but that gets you back to a sphere if you. Well, okay, it's not a sphere at the present time, I guess. But if you
I mean, first an S1 closes off, then another. I mean, first going back in time. I mean.
Yeah. But time has to also come out of it. Ordinary time has to come out of it.
That doesn't seem to be an issue. I'm saying this is the analog of your. So I understand that you you have a ball, right? The lower part of your cup, of your drinking cup.
Yes. Well, it could have a different topology.
Yeah, you have shrunk a sphere, but you can shrink an S1, right?
So there's one simple argument. If you look at well, maybe it's too simple. Maybe one needs to look at it in more detail. Sorry, I need to find it. If you look at
it's not clear that this can work, but I'm saying topologically that one doesn't seem to.
Here's the Friedmann equation. Now we want to go to 0 size, which basically eliminates all the matter contributions. So you're left with this term, which is the Hubble rate, essentially. And then this one is, which is the curvature term. So if there is no curvature, you see, then you find A dot equals 0, which is a singularity again.
Okay.
It can be more complicated than a three-sphere. For instance, you can have, Bianchi 9 and whatever.
If you did this trick though, where you make one circle vanish at a time, I mean, you have to introduce curvature even in order to do that. So you could have no curvature today, but you're not going to be able to one circle that vanish at a time if it's some curvature.
So you have some curvature initially, which then gets diluted, and then the question is by how much can it get diluted? Also, the no boundary proposal tends to give a higher weighting to simpler geometries. Right, so if you, for instance, you look at
as usual with the path integral, the more symmetric.
So the more likely configuration is the more symmetric one. So the three-sphere actually comes out as the most likely one.
Okay, thanks.
Is there a consensus view on how big the universe should be?
No, this is just my opinion here that I presented.
No, I realize what you've been saying, but I mean the rest of the world. The people who would challenge you, is there a or is it just a question to which there is no standard answer?
I think there is no standard answer to this.
But is there a consensus view on whether the universe is currently spatially compact?
No, because we don't see far enough, right?
Well, indeed.
We are limited in how far we can see.
But it is a theoretical bias, if not a consensus.
I'm not aware of a consensus. I see people say different things in different situations. I'm not sure there is an actual consensus on this.
Yeah, I mean, I've seen this at astronomy conferences and people just put in bounds. So each new observation gets some lower bound, and that's all you can say.
Right, exactly, yes. The only way this could have been settled was if we had discovered a non-trivial topology.
Yes, indeed.
But that hasn't been observed. That would have been very nice, by the way, but unfortunately, it just doesn't seem to be that way. Karapet, I think you are...
sorry, yeah. You mean seeing several times the same object, and
yes, exactly.
That would imply compactness?
Yes.
But is it possible that it's compact in one direction but not others?
Well, I would say it has to be ultimately of finite size in all directions. But yeah, in principle, of course, it could also be compact in one direction. I mean, I don't know how you would verify that. You could just say it's compact in one direction, and in the other directions, it has a minimum size.
I mean, we see lots of multiple images of objects. I mean, there's lots of strong lensing out there. So you're looking for something a little more specific to claim that the universe.
Yeah, and these would be coming from completely different directions on the sky.
Yeah.
You're referring to gravitational lensing?
Yeah, so just seeing multiple images isn't sufficient. What you want is some kind of you see an organized pattern or something. I mean, they're looking for something a little more structured.
There's some very nice reviews on this by Luminet, if you want to look at some nice pictures at some point, where it gives examples of what these things could look like. Yeah.
So you didn't mention anything about Vilenkin. So he has this different way of realizing the wave function in the universe.
Yes, that's precisely this way which gives these unstable perturbations.
So so nowadays it is regarded as being disfavored for this reason.
Well, not by him, but I would.
What does he reply? What does he counter to that?
He has tried to make models of perturbations where they are stable. I think the trouble with this is that whatever you do, you always have the gravitational wave perturbations, which are just part of your gravity metric, and they are also unstable in his scenario. And I haven't seen any argument for how you could make those stable. So that's why I think it's not working.
What is unstable waves?
Well, so that the probability is higher to have a higher perturbation, larger perturbation, right? So the trouble is, the bigger the perturbation is, the more likely it is. So the whole thing completely collapses. It's like if you have the stronger your explosion is, the more likely it is. You wouldn't do it very long.
Yeah.
And this thing does not, this is without end, right? So it's the probability would be literally an inverse Gaussian, something like e to the plus field squared. Yeah, so from that you cannot really get any match with observations.
This clearly wants to be done for higher dimensional models. See, see whether they change the picture.
Yes, I agree. Well, we already tried to add a couple of dimensions and some flux, which does work,
Yeah.
and did not significantly change the outcome.
Mhm.
But I agree one should look at more general higher dimensional cases.
This is with whom? Jean-Luc?
With Rahim.
Oh, with Rahim. Oh, I see. You mean our own paper? Okay, that's what you
Yes.
meant. Yeah. Okay. I thought you meant this aspect of it about the finiteness size.
No, not that. Yes. No, that also, of course.
The Kontsevich-Segal-Witten criteria on the complexity of the metric. Is there any elegant way to kind of impose this restriction? It's like I want to have some kind of parametrization, off-shell parametrization of my metric that would automatically satisfy it, so I don't need to care. I just integrate over all the domain that I can.
I don't think people have tried. The trouble is that it's a point-wise criterion, right? So in general, it's very hard to know if some manifold satisfies it or not because you have to check everywhere. That's why you have to do it numerically also. Even in fairly simple cases, you have to do it numerically yeah. But you're right. If one could find some clever parameterization which would automatically ensure that it is satisfied, that would be presumably very useful.
If I've understood it properly, though, Jean-Luc, is it not the case that the Kontsevich-Segal criterion is not simply a law from Trump that you can't integrate this way? It's that if you those path integrals that violate that will give zero because the action is going to diverge. They'll give zero contribution, and so they simply drop out.
Maybe that's one way of seeing it. Yes, but the trouble
is you're allowed to integrate over everything. It's just that not everything contributes.
No, but no. Sorry, it's not. It's the other infinity. It's not e to the minus infinity. It's e to the plus infinity that you get for the path integral. So what you want is precisely e to the minus infinity at large field values. That when the field value goes to infinity, the contribution to the path integral goes to e to the minus infinity.
Oh, okay.
And so you are, and when you don't satisfy this allowability criterion, then you get an e to the plus infinity contribution. So basically, then your path integral is simply not defined.
All right. Yes.
It's not clear at the moment whether you can have. So there are claims of geometries that violate the criterion and are nevertheless supposed to be, fine. I don't know. It seems people take different attitudes to this criterion. It's also, it could be, the criterion comes from putting in all possible p-form fields with all p's. Now, of course, you could also just say, I have a theory in which some kinds of fields simply don't show up, right? So maybe I have a theory in which fundamentally only has two form fields.
Well, you could have 11-dimensional supergravity, which has one.
For instance, yes. And then it could be, the criterion would be different. However, in higher dimensions, typically it gets the criterion gets sort of stronger in a sense, because all dimensions contribute. This hasn't been explored much yet. An additional effect that you have is that if you have a Kaluza-Klein theory, some of your fields in the lower dimensions are actually part of the geometry in the higher dimensions.
Well, indeed, we know that. Yeah.
Yes, and so then then the criterion can sort of change because of that. That's suggesting that maybe this criterion is not the final word yet, because it actually treats gravity and matter fields differently.
Indeed.
And for instance, in supergravity, you would want to treat all fields on the same footing, right? Because they would be, for instance, part of the same supermultiplet. So I guess there should be a more, maybe the ultimate criterion that will come out will be a bit different. But nevertheless, requiring your path integral to be convergent is certainly something you want. I mean, so in that sense, I think there is some use to this.
Just a comment that might not be so relevant, but if these p-form fields are realized in a democratic manner, you write Lagrangians, then independently on the metric, these parts that are f-squared terms, they are on shell 0. I mean, assuming they couple to gravity and everything, but the equations of motion imply that these terms are zero on shell.
Which
So
term? Sorry,
the f squared term that Kontsevich and Segal are using to constrain.
Why would they be zero? Sorry,
on shell. So I'm just assuming that we have some preforms, and we are. I mean, they're written in a way that they are coming with pairs of their dual ones. So it's like scalar. Let's say we are in 4D. We have a scalar field. We have also a two form, and they both enter the f squared terms. But because of their equations are actually that the curvature of one is dual to the curvature of the other. So the square of this curvature plus square of this curvature is on shell zero.
Are you saying the same thing? Is that all supergravities have the feature that their actions vanish on shell?
Kind of.
Their Lagrangians vanish on shell?
It's not the full Lagrangian, sorry. Huh?
Well, the full Lagrangians have that feature without a cosmological constant. All supergravity theories, Lagrangians vanish on shell.
Well, okay, I'm talking about a very concrete example of writing preforms in a duality, I mean, democratic manner, coming with their dual ones. And then the Lagrangian is the square of each curvature plus some topological term where gravity does not contribute. So you would want to just constrain this f squared part where the gravity contributes should be finite as per this constraint. And this part is actually zero there on shell.
I don't see that. Sorry. You can have simply a scalar field and nothing else, and it will not be zero.
Yes, but if you write a theory where your scalar field is accompanied with its dual.
Well, the other fields can be there, but they can all be zero except for the scalar, for instance.
No, I mean if you have a theory where your scalar and its dual enter together and their equations of motion are actually the duality condition.
But that's not generally the case.
Yeah, I mean generally one can write a theory without that. But I mean the statement that I'm trying to make is that if you have fully democratic theories for p-forms, this constraint probably will not be relevant for them. You can have arbitrary complex metric.
You allow for arbitrary coefficients of these terms.
No, they have to be correlated, the coefficients.
For what you say to be true, yes, but not in the Kontsevich-Siegel criterion. They just...
Oh, yeah. I mean, they are doing general, yes, arbitrary. But I'm saying that there are class of theories for which you will not have any strong constraints.
Okay, there might be. Yeah. Okay, so that can, yes. Yes, so that would be an example of a theory where this criterion is simply not relevant. But we don't know if that applies to our universe.
So far, we don't have we don't have democratic description for everything, but for any free field, which is the context here, we have a equivalent description that is democratic. So by using that description, we are able to kind of lift possibly this condition on the metric. In that case, actually, you can kind of sum over any metric, but yeah, for example, if you sum over Euclidean metric, these field configurations will be always trivial on shell, while if you sum over Lorentzian one, it will be non-trivial, but its on-shell action will be zero. On-shell action might not be zero, but the non-zero part will be the topological term that doesn't depend on gravity. So,
well, that's then a special class of theories. I guess one has to see if one can model what we know about the universe with such theories.
Right. Yeah.
Well, I mean, if you're in the real world, we have a U1 in the standard model, and it's got the F wedge star F in it. But then, so the Lagrangian has got a E squared minus B squared, but these don't have to be equal, right? So even
yeah. No, but I'm saying that this F wedge star is the U1 or electromagnetic field. I can write democratically this. So I introduced two vector fields for which I have a different Lagrangian that contains F1 squared plus F2 squared, but on shell star F1 is equal to F2, so this sum will be zero on shell.
Well, I mean, if I just take, so I have F wedge star F and F wedge star F, I could say star F is just F2, and so it's F1 wedge F2, right? That's how you're doing it?
Yeah, I mean, you can write the Lagrangian where you have kind of square of them, and then some topological term. I mean, as Lagrangian, in order to derive the first order equations of quality, you need some other ingredients, including auxiliary fields and the topological term with this auxiliary field. But effectively, you can write a Lagrangian in which you have the two F8 star Fs, and they are on shell dual to each other. F1 star F1 is F2, then yeah, you get F1 wedge F2, but in the other one, star F2 is minus F1, so you get the minus F wedge star F2, so they cancel each other.
Ah, okay. And so that's different from the standard model, the way the UN comes in.
Yeah, sure, it's different.
Okay.
Whether we can rewrite all of the standard model in the democratic language is an open question.
Well, but it would imply that the Lagrangian was zero, you're saying, but that...
No, it's only
the form part. Okay,
on
so I guess
shell, huh?
Only the pure form part gives you zero, you're saying.
Yes, and only on shell.
Yeah.